Hi, I'm Fatma Shehab. I'm a postgraduate student at Kuwait University. I'm doing Masters in Mechanical Engineering at the College of Engineering and Petroleum. This research is a part of the MS degree requirements, and I worked on this research with my supervisor, Dr. Majid Majid, and my co-supervisor, Dr. Jasim Baroun. And the research was funded by the Office of Vice President for Research. The title of the research is Deformations of Cured Laminated Composite Plates Having a Misaligned Layer Using Finite Element Analysis. First thing, I will give a brief introduction about composites. A composite material is a combination of two or more materials combined in order to give a new enhanced material of different properties. Composites, they have two different materials. One of them is called the reinforcement and the other one is the matrix. The reinforcement is embedded inside the matrix in order to make it stronger, and it comes in different forms like particles, short fibers, long fibers, or flakes. And the matrix is, it acts like a glue. It holds the fibers together and it creates dimension and structure to the material. The type of composites we are studying here is laminated composites, where the final product is laminate, that's shown right here. That is shown right here. It's made up by laminating composite layers on top of each other, and each layer has fibers oriented at a particular direction or angle, theta, and the layers are very thin, like in micrometers. The fabrication of these laminates involves several processes, starting from the fiber placement, where fiber layers are hand-laid manually in a mold by stacking them on top of each other at particular orientation. Then the resin epoxy matrix is poured on these layers. Then the whole assembly is placed inside. It goes through the thermal curing process, where it is placed inside the autoclave chamber, which is like a high temperature pressures. Now here we are studying symmetric laminates, which means that the layers above the mid plane, which is shown in red, a mirror image of the layers below the mid plane. So these laminates, because of symmetry, they come out of the autoclave at the highest temperature flat, and they remain flat after they cool down to room temperature. However, if there is a misaligned layer, especially that the fiber placement is done manually by hand, so there's a big chance of misalignment. So if there is a misaligned layer in this symmetric stacking sequence, it will become unsymmetric. So during the cooling process, the shrinkage will not be uniform and it will deform to a non-flat configuration. It will wrap, or they call it spring-in effect. So we looked through literature and we found that 2 to 3 degrees fiber misalignment is highly probable. So this motivated us to study this problem. We want to know what to the deformed shape or the post-cure shapes of the laminate if there is misalignment in one of the layers. How is that going to affect the deformed shape? And what is the allowable degree of misalignment? Is 1 degree misalignment allowable? Is 2 degrees allowable? And what will happen if the misalignment is in the first layer, or the second layer, or the last layer, which will affect more? Or are they going to be the same? And also we want to know, is the stacking sequence important? The stacking sequence is the arrangement of the ply angles of each layer. So is it important? Is there a stacking sequence that is less affected by the misalignment? So these are our objectives. We studied this problem using the finite element method, using a Abacus software. This is the model. It's a 2D model with shell elements. It's a square plate clamped at the midpoint and free to move everywhere else. At the first step, we applied a temperature change to simulate the cooling from curing temperature to room temperature. And if the resulting shape was unstable, we did follow by another dynamic implicit step where we applied a pressure to the whole laminate for an instance and released it just to let the laminate vibrate from its unstable position to reach one of the stable positions. Usually there are two stable positions with a snap-through phenomena between them. Like you snap it from one stable position, it will go to the other stable position. We did validate our model using different benchmark studies that are listed here, 3 different studies. And we found that our model could predict correct and accurate results. We also did a mesh sensitivity analysis to obtain the optimum mesh size in order to use it for further simulations. So we focused our study on cross-ply families, cross-ply laminates, which means they are fabricated from layers oriented at 0 degrees or 90 degrees only. Because these are the most frequently used in industry. So we studied all possible cross-ply 8-layer symmetric laminates, which were 14 different stacking sequences. We introduced a range of misalignment delta theta in each of the layers for each of the one at a time, a layer at a time, for each of these 14 stacking sequences. Of course, if there is 2 layers that have misalignment, then this is a completely different study. Here we are only studying one misaligned layer. Moving to the results, first thing, we found that for small fiber misalignment, like for example here, 5 degrees misalignment, the post-cure shape looks like this. The maximum and minimum deflections happen or occur at the corners of the laminate. We also found that the deflection of the upper right corner is equal to the deflection of the lower left corner and vice versa. Here, for example, for 5 degrees misalignment, the deflection of the corner was about 2 times the thickness of the laminate. Then we introduced a 90 degrees range of misalignment from minus 90 to 90 degrees with 5 degrees increment. Of course, the 90-degree range is extremely large and it's impractical. But we need to understand the behavior of the laminate. How is it going to deform? So, for example, this graph shows the misalignment introduced in the first layer of this stacking sequence. There's another graph for the second layer and another graph for the third layer and so on. And similar graphs for the other 13 stacking sequence. So a considerable amount of simulations were done and it took so much time and effort. For example, from here we noticed that for minus 10 to 10 degrees range of misalignment, the shape will look like this. The maximum and minimum occur at the corners. However, for example, looking at this line, when the fiber misalignment is about 60, the deflection can reach about 70 times the thickness of the laminate, which is very huge. And of course, the shape changes. It looks like a twisted cylindrical shape and then a cylindrical shape, so it's not fixed. These are the results for 7 of the 14 stacking sequences, the deformation results. We noticed that the other 7 stacking sequences obtained exactly the same results, so they can be reduced into only 7 because the other 7 are the rotated versions of these 7 stacking sequences. Furthermore, we noticed that for a range of misalignment from 10 degrees to minus 10 degrees, the maximum is about here 12 times the thickness of the laminate. We also noticed that even a slight fiber misalignment, for example, here, 1 degree misalignment can result in about 4 times the thickness of the laminate, deformation of about 4 times thicknesses. So it's huge. We also expected that misalignments in layers further from the midplane would cause deformations that are higher than the same degree of misalignments in layers closer to the midplane. However, we found that this is not always true. For example, looking at this stacking sequence, the deformation in the second layer is always higher than the same deformation in the first layer. And also here, the deformation in the third layer is always higher than the misalignment in the first layer and the second layer. So these are our main conclusions. At the end, I would like to thank you for listening, and I would like to thank my supervisor who helped me and took so much from his time. I would also like to thank my parents and my sister. And if you have any question, you can contact me through this email, and this is my phone number. I will be happy to answer any of your questions. Thank you.